by topic. We're going to start a new topic today. We're going to start looking at rates of reactions. Now, rates of reactions are fairly easy sort of things, and you do various experiments with those, GCSE, and you then move on to looking at these in a little bit more detail. And what we're going to do is start having a look at some of these rates of reactions and basically what they mean. So let's not do an experiment, but let's go and have a look at one I've done already. Now, what I've done is I've got a calorimeter, and the calorimeter simply consists of a space where we can put a tube. This is called a cuvette, and what we have is a light source here of particular wavelength, and we have here a detector. The light goes through here, and we measure either how much light is absorbed or how much light goes through. Transmittance. Now, I've already decided on an experiment, and I looked at a substance called sodium thiosulfate, and I reacted that with some HCl. I decided to use 1 centimetre cubed of HCl each time, and I reacted it with different amounts of thiosulfate. So I took 1 centimetre cubed of a 0.1 molar solution of thiosulfate, and I added to that 4 centimetre cubed of water, and we did the experiment and we got a curve. I then repeated the experiment, this time with 2 centimetre cubed of the thiosulfate and 3 of water, then 3 of the thiosulfate and 2 of water, 4 centimetre cubed of thiosulfate and 1 of water, and then just with 5 centimetre cubed of thiosulfate and 0 water. And what did I get? Well, I got something which looked remarkably like this set of curves. So the long blue line is the first experiment that I did, where the mouse cursor is. That is using the weakest solution, and then here slightly stronger, that's the 2, the 3, the 4 and the 5. So I have now got my measure here of what's going on in the reaction. And what I can do with this is I can put a little ruler along here, and I can measure the rate of the reaction. And if I get to about there, that's the highest rate of my reaction. So I found the point where I've got the greatest rate of reaction, and so that's 0.5. Looking at the next one, then I managed to get that to about 1.2 there. Looking at the third value, back 2.1. I'm just going to move these around a little bit so we can see, and then 3.0, 3.1, 3.1, Does seem about 3.1 there. And finally on my last one, about 4.9. So we've got some sort of relationship here, and I could put these in a bit better order here. And there are my rates of my reactions, my fastest reactions. Okay, so we can look at a reaction, we can see that if we add more, it's going to go faster. Now, what we do have are things called orders of reactions. So the order of a reaction, a measure, if you like, of the rate and how it's actually working. So by changing the concentration here, we change the rate of a reaction. So let's have a look at this. So we can say that a rate of reaction here is basically going to be proportional to the reactant, and it might be reactant A here, and it depends on how much I've got, and we can give that to the power n, how much we've got. In a reaction, different reactants can have different orders, ways that they work, and how that affects the way they collide and what they do. So we've got, first of all, a zero order reaction. Now, what does a zero order reaction tell me? Well, a zero order is that when the concentration here has no effect, done stern voice there for you, it has no effect on the rate. So you can bung more in, take it out, it seems to have little effect. Because basically, if we think of any number raised to the power of 0 is going to be 1. The concentration, in other words, does not have any effect on the rate. Our next one is we could have a first order reaction. And basically, when we've got this, if you double the concentration, then you basically double the rate of the reaction. If you triple the concentration, you would triple the rate of the reaction, and similar. And then we get a second order reaction. So in this way, if the concentration is doubled, then this will increase by a factor of 2 squared, or it'll be 4 times faster. If you triple it, then it would go up by 2 here, sorry, 3 here to the 2, which will give us 9 times faster. The overall order of a reaction basically is related to the orders of the individual parts of the reaction. So the overall order is the sum of the orders. So if I've got here a rate, and this is proportional to the concentration of A and the concentration of B, then we could write that rate as being equal to some constant times the rate of this reaction to whatever power there is, and the other one to the other power. And the overall order will be m plus n. Let's have a look and see what we can actually do with this. But first, I've got to worry about units, and units do cause a little bit of problem, and generally in most exam questions there's normally a mark for getting the units right, so it's worth a mark to you, so it's worthwhile having a go at trying to do this. So let's suppose I've got here a rate order of 0. So we know my rate is going to be proportional to, I'm going to say equal some sort of constant of my concentration, I don't care what it is, so that will become equal just to K. So K is the rate of the reaction, and this is measured in moles decimeter cubed per second. So moles per decimeter cubed per second. If we've got an order of 1, then my rate equals some constant a to the 1. If I rearrange this, K equals the rate divided by a to the 1, and that gives me these moles per decimeter cubed per second over moles decimeter cubed per second. They cancel out, and basically we're just going to have the units of seconds per second. And if I have an order of 2, then my rate here is proportional to equals K, my system times this one squared. So K is going to equal the rate over a squared. So that's going to give me moles per decimeter cubed seconds over the concentration, which would be moles decimeter cubed and moles decimeter cubed. That cancels with that, so my units here weirdly are going to be decimeters cubed per mole per second. Ugh, not nice. Just trying to think about how to do those, but they do simply cancel out, and it does give us something. So we've done an experiment. And what we've done, we've continually monitored an experiment. I didn't want the calculator, I wanted that screen. And as my experiment goes on, so we can see that it starts off at 100. Just get it to fit in for you. And we can see we've got this set of rates. So I've measured my experiment, and sometimes we can do an experiment like this where we've got a change. Other times we might want to do this slightly differently, and what we might do, for instance, is if we take a particular reaction, one with a color change, so let's take something like propanone here, and if I react that with iodine again, or aqueous, this is going to give me my CH3 CO CH2I, which is now colourless. And I've got a reaction. As the reaction proceeds, this iodine's used up, which is orangey brown colour, and it becomes clear. So we could measure this using one of these simple colorimeters to work out. So if I want to try and work out what's going on, if I prepared different standard solutions of iodine, and if I now react those, what I would get is a graph of, let's say, absorption here, and we've got concentration here. Very badly written there for you. And we would get, perhaps, with values on the line there, different concentrations, different amount of absorption. Now if I take in my cuvette here an unknown solution of iodine in there, then it might come up with a particular value, and that particular value then I can calculate exactly where it's going to be on the graph. If we start looking at concentration time graphs, then we get basically a couple of types to have a look at. If I measure perhaps here concentration, and I measure it against time, if I've got a zero order reaction, then it's going to look something like this. So this is our zero rate. Whereas if I'm going to look at a first order rate of reaction, then it's going to look more like that. The second order reaction, if I got one of those, basically the downward curve should be steeper but tailing off more slowly. So for my second order reaction, it's probably going to look more like this. Not too easy to tell those apart. but there are ways that we can do this, and we'll have a look at some of those now. But just before we do that, I want to look at something which comes in physics and various other places, biology, all of them. They do half-life, and a half-life curve is an interesting one. So let's just draw in sort of a half-life curve. Half-life curve typically is going to look something like this, and if we take some sort of arbitrary measurement, I'm going to put 4 there, let's put 2 there, 1, I'm going to put a half there, and if I've drawn this correctly, then my 4 will be there, go across to my 2. Please bear in mind my half-life curve was just guessed, but if we then go across to the 1, we can see that this should be, if I've done it properly, the same distance. And if I were to try a half, and you can see that it obviously isn't in this case, but they should be the same distance, and that's because I've drawn that by eye rather than doing a proper half-life curve. So we've got the idea of this half-life curve. In a time, half of the amount of a substance will disappear, and this is going to be something like a first order reaction. Let's take a look at the data that I've managed to get on my graph. Now, I haven't got a direct measurement of my concentration here. Press the wrong button. What I've got is, I've got, when we've got a concentration of 1 lot of thiosulfate out of 5, then we got a number up there of 0.5. When I had 2 units of thiosulfate in my 5 in the cuvette, then basically we're looking at a number 1.2. These are all minus. When we come and look at 3/5, then looking at the graph, I've got 2.2, 4/5, you can see we're at 3.1, and finally at 5/5 I'm at a level of 4.9. So this is measuring my rates of my reaction. I've got here a feeling for my concentration. It's not measured exactly. I could work it out exactly because I do know that I've got 0.1 molar sodium thiosulfate, and I've got of that 1 centimeter cubed. 2, 3, 4 and 5. Let's see if we can have a look at what's going to happen here if I try and plot a graph of this. So let's try plotting a graph of the rate and I'm going to plot that against my concentration. Now what I'm going to do is a very crude graph here. I'll make that one a bit longer. Right, so let's see, let's set up some parameters here and see what we've got. So I'm going to plot my rate along this side, and my rate is going to go from 0, 1, 2, 3, 4, 5, and we're going to have my concentration along the bottom, which is going to give me my 1/5, 2/5, 3/5, 4/5, and 5/5. So let's get a feeling for what we've got. So at 1/5 I've got, I'll plot them in a different colour, a half. At 2/5 we've got 1.2. At 3/5 we've got about 2.2. At 4/5 we've got about 3.1, and 5/5 we've got about, just trying to get this about right there, about 4.9. And what have we got here? Well, we can see that I've now got a rate graph, and this rate graph, just drawing what I've got, is looking like a curve. It's not looking quite like a straight line, although putting these points on here, I could argue here we have got, within the bounds of a little error, a reasonable straight line there. How can I tell better what's going on? Because curves are notoriously difficult to have a look at in science, and in fact what we can do is we can try and work out these in a better way, and that is by logging the data. Right. Popular. Right, okay, so what I'm going to do is I'm going to try now to have a look at the log of those. Now what we're going to try and plot? Well, let's try and plot the log of both, and we'll see what we can do with those. So let's remind ourselves of the values that we've got and see if we can work out the logs of these numbers. So I've got these numbers, and what we can do is we can work out on the calculator the logs of these. So let's work out, first of all then, going on the calculator, I want to work out the log of 1/5. That didn't help me because, let's just take it out. Log to the base 10 here, and what I want to do is put in a 5th. There we are. So the log of a 5th here is going to give me minus 0.69. and I can record that here. Now what we can do is we can work out the values of all of these, and all I've got to do really to make my life easier is just go and edit that and put in 2, which gives me minus 0.39, really 0.4, but still, let's go and edit this back. Then I've got 3/5 minus 0.22. Then we can do the next one, which is this time going to be 4/5 minus 0.9 minus 0.09, and finally we can work out 5/5, which is the log of 1, and something that you may be good at doing, or possibly not if you're not very good at maths, is log of 1, which gives us 0. So we've managed to get our values here for our concentration, and what we're going to do is exactly the same with the logs of the other ones. So let's just see if I can go back, and basically let's just take out all that, because I've just got to put in here 0.5, .03010. Let's edit again, and we've got to put in 1.2. My next one is 2.2. We can then edit the last couple, which are going to be 3.1. And finally, I've got 4.9. So that's given me a different set of values that we can plot. This here is my rate, the log of my rate, and I've got the log of my concentration. So let's see if we can plot these. Got a very different scale to play around with, but we're still going to put here the log of the rate going up, and we're going to have the log of the concentration going along the bottom. So my values here are going to go from minus 0.3 to virtually 1. So if we shove here 0, and we go 2, 4, 6, 8. And then that's the concentration. I've done it wrong. I wasn't looking what I was doing. I've just put the rate numbers in. We'll survive. 0, 0.2, 0.4, 0.6, 0.8, and when you're not looking what you're doing, it doesn't help. So this is going to go from 0, and I've got to go minus, so up to 0.7, so minus 0.2, minus 0.4, minus 0.6, minus 0.8. Let's have a look and see what we've got. I could have plotted this the other way round, but I'm not going to bother. It's still going to work if it's going to work. So, taking my values, then at minus 0.69, which is going to be about there, we've got there. I've got a rate of about minus 0.3, so it's going to go there. Let's try the next one. You notice I'm not even plotting this very accurately. Log of concentration is 0.39, it's going to be about there, and we're going to get 0.079, so that's about there. We're going to end up with my next one, which is my concentration of 0.22. It's going to be about there. Going to go up to 0.49. And you can see we're not going to get a straight line here. And we're going to get 0.09. We're going to get about that was 4.9. The other one was 3.4. Making a mess because I can't. I'm doing this in a hurry. And we've got about 0.69 here and 0. Well, I am achieving very much a straight line there rather than an actual curve, and maybe this value is perhaps wrong, or maybe with as little data as I've got, maybe this still is a curve going through there, within the realms of me graphing this pretty badly on a piece of paper rather than perhaps doing it on anything better like graph paper and taking the figures and playing around a little bit more. So we've got the idea of how we're going to do one of these types of reactions. Now, what we need to do is have a look at some reactions. And the reaction that I liked when I started doing all of this, that got me into chemistry, was the one called the Iodine Clock. And we'll put a link in the description here to the Iodine Clock experiment. When you start playing around with the Iodine Clock, and for those of you who don't know what the Iodine Clock is, it is one of the most exciting experiments that I've ever met in chemistry, where you pour two clear liquids together, leave it, and instantly it turns black. So it's a reaction that takes an amount of time. It's got a very fast reaction and it's got a very slow reaction, and this makes life interesting. And more about that one next time. We'll have a look at the Iodine Clock for next time. So those are sort of interesting experiments. I watched Professor Sir George Porter do that for me when I was a child, and I watched this with great interest to see this experiment where two liquids suddenly became black, and I thought, I want to do this one. And I had to wait till I was about 16, 17 before I got the opportunity to try out the Iodine Clock for myself. And fascinating experiment, a lot of fun. So let's go back, however, where we are looking at concentration time graphs. We're looking at this idea of when something reacts, it's taking some time to go, and we can work out zero order and other things, first order, second order. Determining this is quite difficult, as you can see that by taking my experimental data, then I've got to try and work this out. And if I repeat this experiment several times, then what I can do is find that when we do this several times, we get not necessarily quite the same results. This is an experiment done by another student, and we can see that my 0.5 coming up again, my next one 0.1, next one 0.18, next one 2.8, and the last one, whoa, 4. I can see that when I'm trying to do this, that maybe the values are a half, 1, 2, 3, 4. That's what they are approximating to. And I'm getting different amounts when I try these. So when we play around with these, what we should see is if we've got a zero order reaction, and this is now playing with the logs of these, then I would expect a zero order to be like that. And we're plotting here the rate here against concentration. If I can put in my first order reaction, then as one doubles, so the reaction doubles. And that is what I think I'm seeing with my thiosulfate reaction, although the numbers aren't quite accurate enough to try and sort of determine what's going on. I better label that one first order for you. And then finally we've got rate of concentration, to give me a second order reaction. First order, second order. Let's try and have a look at those. Zero are a bit boring really. So it's generally our first and our second orders that are going to do what we want to do with them. That's playing around with concentration. How about temperature? Well, if we do this with temperature, we can find that we get a similar set of reactions as we see here. And I can make a similar type of curve if we play around with these temperatures. That as I keep the concentration, as I keep everything else the same, but we change the temperature, then at the lower temperature, then the rate of the reaction is going to be slower. So there we've got an introduction to rates, we've got some idea of some units, we've got some idea of what the graphs look like, and we can see that when I do an experiment that it doesn't necessarily quite work, but then that's the problem when you do experiments, they don't always work quite as you want. In the next one we'll try and have a look at, as I say, the iodine clock experiment, and we'll have a look and try and see how this experiment goes. So if you enjoyed what we did today and found it interesting, then please subscribe, and I will see you again on the next A-level chemistry topic by topic. Bye bye, take care.